Hello dear students, my name is Rajkumar. Today we will be discussing about a topic called rolling motion of rotational mechanics chapter. These topics become important because a lot of questions are asked in JEE Mains as well as JEE Advanced from this topic. So in this class we will discuss what is rolling motion, um, how to write equations for rolling motion, and we will also discuss about some JEE Mains PYQ regarding this topic. So let's start our class. So first of all, let's understand what is rolling motion. First of all, let's understand what is rolling motion. So rolling motion is nothing but a combination of, it is a combination of rotational and translational motion. Rotational and translational motion. Okay. Rotational and translational motion. Suppose we have a rigid body and this is the center of mass of this body. The center of mass is moving ahead with linear speed v, and the body is also rotating with angular speed omega about its center of mass. So in this case we can say that body is in translational as well as rotational motion. So this is a case of rolling motion. Now let's discuss about some points. Suppose you have a rolling sphere whose center is moving ahead with linear speed v and which is rotating with angular speed omega. So if we talk about the topmost point and the bottom point of this rolling body, this point will acquire both the motion of translational and rotational motion of this body. That is, this point, suppose this point is p and this point is q. The point p will be moving ahead with net speed v plus omega r, and point q will be moving ahead with v minus omega r. This has to be understood. After that part, if we talk about total kinetic energy of rolling body, suppose a body is in rolling motion, so its total kinetic energy is given by basically rotational kinetic energy plus translational kinetic energy, that is k translational plus k rotational. So basically it will come, if the mass of this rigid body is m, which is moving with linear speed v, its translational kinetic energy will be half mv square plus its rotational kinetic energy will be half I omega square. So if we do understand, suppose a rigid body which is rotating about this axis, this axis is called axis of rotation. So I is basically moment of inertia. And omega is its angular speed. Omega is its angular speed. Okay. So this is the total kinetic energy of a rolling body. We have to understand it. Now let's move ahead. In case of pure rolling motion, let's discuss about what is pure rolling. If we to talk about pure rolling motion, suppose we have a rolling body whose center is moving ahead with linear speed v and which is rotating with angular speed omega. The radius of this rolling body is r. Okay. So the bottom point has translational speed of v minus omega r. In case of pure rolling, the contact point of a moving body should be at relative rest. The contact point of a rolling body with the surface should be at relative rest with the surface. The contact point of rolling body should be at relative rest to the surface. The point of the rolling body which is in contact with the surface is, let's talk about this point P. This point should be at relative rest with the surface. Like say if the surface is at rest, that is v equal to 0, this point also should have a zero velocity. Basically the contact point should be at relative rest with the contact surface. So we can write that v minus omega r equal to 0. Here we get v equal to omega. So this is the very necessary condition for a body to be in pure rolling. After differentiating this equation, we can also get a equal to alpha r. A equal to alpha r. Suppose there are forces acting on this rolling body, so the body will acquire some translational acceleration, and so body will also acquire some angular acceleration. So this is the relation between translational and angular acceleration of rolling body, and this is the relation between linear speed and angular speed of rolling body. So these are the conditions we required for a rolling body, pure rolling motion. Now what are the dynamics of rolling motion? Let's talk about dynamics of rolling motion. Dynamics of rolling motion. So here we can see that suppose there is a rigid body, some forces are acting on this body, like suppose there is a force F1 acting this way, there is an F2 force acting this way, and this is the center of mass of this body. So resultant of these forces F net will provide an translational acceleration in this body. At the same time, the torque of these forces will provide an angular acceleration in this body. So we have to write two equations, one for translational motion and one for rotational motion. The translational equation is quite simple, that is net force acting on this body is equal to mass of the body into acceleration of center of mass of this body. So this is the translational equation for rolling motion. Apart from that, for rotational equation we will calculate the torque, individual torque due to all the forces, and sum them to find the resultant torque. So the total torque acting on this rolling body will be equal to moment of inertia into angular acceleration. So this is the rotational motion equation. So using these two equations we can solve almost 90% or we can say 100% of rolling motion problems. Okay, let's move ahead. From moving ahead, first of all let's discuss about moment of inertia of some common and standard bodies. Like if you talk about ring, its moment of inertia is basically mr square. If you talk about disc, its moment of inertia is 1 by 2 mr square. If you talk about hollow cylinder, its moment of inertia is mr square. If you talk about solid cylinder, its moment of inertia is 1 by 2 mr square. For a hollow sphere, moment of inertia is 2 by 3 mr square, and solid sphere it is 2 by 5 mr square. Okay, so moment of inertia can be written as c into mr square. By comparing this, we can write for every body that for ring the c equal to 1, for disc c equal to 1 by 2, for hollow cylinder c equal to 1, for solid cylinder c equal to 1 by 2, for hollow sphere c equal to 2 by 3, and for solid sphere c equal to 2 by 5. We can understand these points. Now let's move ahead. Let's take some questions. Suppose we have a solid sphere. This is a solid sphere, and this is placed on a rough horizontal surface. This sphere is placed on a rough surface. Okay, now consider about some forces acting on this spherical body. Suppose a force is acting about its center. This is external force F. Okay, so this force will produce an angular acceleration in this body. We are getting that. Okay, mass of this sphere, let's say m, and radius of this sphere, let's say r. Okay, So this external force will produce an translational acceleration in this body. Okay, so due to translational acceleration, the body will move ahead, and there will come and relative motion between point of contact and surface of this body. So a friction will start acting on this body in backward direction, and this frictional force will provide an torque, and the body will start rotating about its center of mass. So the body will get in some angular acceleration alpha. We can understand these points. Now we will simply write equations of motions for this rolling body. We simply have to use two equations, that is net force acting on body is equal to mass times acceleration, and total net torque acting on body is equal to moment of inertia into angular acceleration. Also, since this is the case of pure rolling, motion, we can write that translational acceleration is equal to radius times angular acceleration. This is the condition for pure rolling we will be using here. Okay, one thing we must have to consider that friction is a force. Friction always tries to make the body in pure rolling. Friction always try to make the body in pure rolling. We have to understand this point. Okay, fine. Now let's move ahead. Let's write some equations. Okay, what is the net force acting on this body? We can see that on this body two forces are acting. One is external force F in forward direction, one is frictional force in backward direction. So the net force will be F minus F equal to mass into acceleration, m into a. Okay, now let's talk about the second equation. We can see that this external force F is passing through the center, so this will not produce any kind of torque. The only torque will be produced by this frictional force, and we can write that frictional force into radius. We have to take the perpendicular distance, this distance, which is equal to radius. F into r equal to I into alpha, and since this is a solid sphere, its moment of inertia is 2 by 5 mr square. Let's write it here. Okay, so we can write that for this equation, frictional force into radius equal to 2 by 5 mr square, and for alpha we can write it as a by r. Alpha can be written as a by r, so we can write it as a by r. Okay, this r and this r cancels out, finally we get that our frictional force comes as F equal to 2 by 5 ma. Now what we will do, we will put this value of friction in this equation, like here, to solve this problem. So we can write that F minus 2 by 5 ma equal to ma, where we are getting F equal to ma plus 2 by 5 ma. So this is basically 7 by 5 ma, and this is F. So here we can say that our acceleration is becoming 5f by 7m. Also we can write angular acceleration alpha as a upon r, so this solved as 5f by 7mr. Okay, now someone will be asking for what is the frictional force. So frictional force acting on this body F equal to 2 by 5 ma, this equation 2 by 5 ma. The 2 by 5 m into 5f by 7m, m and m cancels out, and we get our result as 2f by 7. So this is the frictional force acting on this body, rolling body, and all these forces ensure that our body is in pure rolling. Okay, since this is a kind of pure rolling, the point of contact is at relative rest with respect to surface. So if someone asks which kind of friction it is being acted here, so this will be static friction. We have to understand it. In case of pure rolling, frictional force is always static. Okay, fine. Now let's discuss some problems on inclined planes. So Let's discuss some inclined problems. Suppose we have an inclined surface. Suppose we have an inclined surface whose angle of inclination is theta, and we have a rolling body here. Our surface is rough. Our surface is rough, and it can provide enough frictional force so that body can maintain its pure rolling. Okay. Let the mass of this body is m, radius of this body is r, and its moment of inertia is I. Moment of inertia of this body, moment of inertia is equal to I. Okay, fine, no problem. Okay, what are the forces acting on this body? Let's discuss. One force acting is mg, vertically downward. Okay, and one force acting on this body is normal force. The another force acting on this body is normal force, this way. This is the normal force acting on this body. Okay. So what we can do, we can just resolve this mg in two components. One is normal to incline, that is, this is theta, so this is theta. This is mg cos theta, and this is mg sin theta. Now mg cos theta and normal force will balance out each other, so they will not affect any kind of acceleration in this body. They will not produce any kind of acceleration. Also, these forces are passing through the center of this rolling body, so they will not produce any kind of torque. The only acceleration produced will be due to mg sin theta, which is acting downward, and this force will let the body accelerate in downward direction. Okay, due to this acceleration, at the point of contact, surface will apply a frictional force on this body. And this frictional force is provide a torque, and the body will start rotating as well. Its angular acceleration is alpha. So in this way the body will start its rolling motion. Now let's move ahead. Write our equations. Let's write the equations. We can see that how many forces are acting along the incline. One force is mg sin theta and other force is F. So we can write that mg sin theta minus F equal to m into A. This is our first equation. Second equation, we can write that let's consider about the torque forces. Mg sin theta, mg cos theta, and normal force, all these forces are passing through the center of body, so they will not produce any kind of torque. The only torque will be produced by this frictional force. So we can write that frictional force into radius equal to I into alpha, and also we can write alpha as A by R. Acceleration by radius. Okay, so we can write F equal to I into A by R, or this R will come here, so this will be written as F equal to I A upon R square. Okay, now let's put this value of friction here in equation 1. Let's see what we are getting. So we can write as mg sin theta minus I A by R square equal to ma. We can here write as okay, fine, mg sin theta equal to A m plus I by R square. Okay, so mg sin theta equal to A into m 1 plus I by mr square. So m and m cancels out. Our acceleration 2 comes as A equal to g sin theta by 1 plus I by mr square. This is the acceleration produced in a rolling body when placed over an inclined surface. Okay. This is our relation. This is our relation. Also we can find our frictional force. We have to simply just put the value of acceleration in the above equation and we will get our um, uh, frictional force. Alpha can be written as a by r, so we can put the value and get our result. Okay, now let's assume that the length of this inclined plane is L. Let's assume that the length of this inclined plane is L. This length is basically L. So we basically want to find that what should be the velocity of this body, what should be velocity of this rolling body when it reaches the bottom point of this incline, when it reaches the bottom point of incline here. Okay, we want to find its linear speed v. So what we can do is, we know the length of this incline, we simply write the equation. We can write this equation that v square equal to u square plus 2as. This is the equation of motion we can apply to find the final speed of this rolling body when it reaches the bottom point. So v square we can write as initial speed was 0 square plus 2. Acceleration we have find out somehow 2g sin theta by 1 plus I by mr square, 1 plus I mr square into s. For displacement we can take the length of this inclined plane, that is L into L. So our final velocity is given as root under 2gl sin theta root under 1 plus I by mr square, 1 plus I by mr square. This is our final velocity when the rolling body reaches the bottom of incline. Okay, here we can see one thing, that v square is proportional to sin theta. And most of the problems we can use this relation to find quick results if the problem is based on this pattern. Okay, let's discuss some problems on JEE Mains previous year questions and see if we are able to solve such kind of problems or not. So let's talk about this problem. First of all, let me copy and paste it somewhere. Okay, so let's discuss it further. Okay, so here we are given a question. A solid sphere is rolling without slipping on a horizontal plane. We are given an horizontal plane. This is a horizontal plane. We are given a solid sphere. Which is rolling without slipping. If the problem is saying that it is rolling without slipping, it basically says that this is a case of what? This is a case of pure rolling. This is a case of pure rolling motion. We have to understand it. Okay, now let's move ahead. Fine. So in this problem it is given that the solid sphere, let's the mass of a sphere be m and radius of this sphere be r. Okay, so it is in pure rolling motion. We have to understand it. Okay, the question is asked, what is the ratio of linear kinetic energy of this center of mass and of the sphere and rotational kinetic energy? See, we have seen this kind of concepts earlier. We have told that total kinetic energy consists of two types, that is, one is rotational, plus one is translational. That is half I omega square for rotational and half mv square for translational. Okay, so in this problem we are asked about the ratio of these kinetic energies. Okay, since the body is in pure rolling, if its angular speed is omega and center of mass linear speed is v, we can say that v equal to omega r. We will be using this relation, so on. Okay, also it is given that it is a solid sphere. This is a what? This is a solid sphere. Okay, So for solid sphere we know that moment of inertia is 2 by 5 mr square. 2 by 5 mr square we will be using it. Let's talk about k translational. So translational kinetic energy is half mv square, no problem. For rotational kinetic energy we will write half I omega square. So this becomes moment of inertia becomes 2 by 5 mr square, and for omega we can write as omega equal to v upon r. This is the condition for pure rolling motion. So this will become v square upon r square. This cancels out. So our final result becomes 1 by 5 mv square. This is the rotational kinetic energy. In this problem we are asked for the ratio of linear kinetic energy and rotational kinetic energy. So we are asked about a translational kinetic energy and rotational kinetic energy ratio. So it comes like half mv square whole divided by 1 by 5 mv square. So mv square cancels out, and the final result is basically 5 by 2. So the correct answer will be option C, 5 by 2. Let's move ahead. Let's talk about some more JEE Mains PYQ. Let's talk about the second question, that is this one. Okay, in this problem we are given that this is question number 2. In this problem we are given a circular ring and a solid sphere having same radius rolls down an inclined plane from rest without slipping. Okay, so first of all let's draw our inclined plane. Okay, so in first case a ring is basically moving down, ring is rolling down. Okay, this is a ring rolling down. And in second case we can see that a solid sphere is rolling down. This is a solid sphere is rolling down. Okay, both have same radius, both ring and solid sphere have same radius, inclined plane. The ratio of their velocity when reaches at the bottom of the plane is, okay, we know that when the body reaches the bottom it has a linear speed v, which is given by v equal to root under 2gl sine theta divided by 1 plus I by mr square. Okay, fine. Okay, the incline is same. We can say that for both the bodies the inclined plane is same, that is the angle is same, theta is same for both the bodies. This length is also same, for this body. What not same here is their moment of inertia. We have to understand that for a ring moment of inertia is basically mr square, and for a solid sphere moment of inertia is 2 by 5 mr square. Okay, so if we talk about velocity of ring, we will be getting root under 2gl sine theta whole divided by 1 plus mr square by mr square. So this is solved as root under 2gl sine theta by 2. This cancels out, and our result we get as root under gl sine theta. At the same way, velocity of a sphere we will get as root under 2gl sine theta by 1 plus 2 by 5 mr square by mr square. So here we will get root under 2gl sine theta by 7. This will be 5 by 7. Okay, no problem. Okay, let's solve it. We are asked about ratio of velocities when they reach the bottom of the plane is this root x by 5. Okay, so we have to find the ratio of ring and to the uh, solid sphere. The velocity of ring by velocity of solid sphere, we get velocity of ring by velocity of solid sphere, we are getting root under gl sin theta by root under 10 gl sin theta by 7. Okay, so after solving it, we will get 7 gl sin theta by 7 gl sin theta by 10 gl sin theta. So gl sin theta cancels out. We are getting our result as root under 7 by 10. Okay, now comparing this result with root under x by 5. Okay, root under 7 by 10 equal to root under x by 5. We get as x by 5 equal to 7 by 10. 5 से 10 to 2, x equal to 7 by 2, which is 3.5. X equal to 3.5. This is our result. This is an integer based question. So after rounding off, we will be give our result as 4. Okay, now let's talk about the last question we will discuss today, and this is, let's talk about this problem one. Okay, let's read this question. In this problem, it is given that a solid sphere of mass m, and radius r is allowed to roll without slipping from the highest point of an inclined plane of length L and makes an angle 30 degree with horizontal. Okay, so let's draw our diagram. We are given an solid sphere. This is an inclined plane, and angle of inclination is 30 degree. We are given here a solid sphere which is rolling down. Okay, and after reaching here, it gains an linear speed v1. After reaching here, this solid sphere gains a linear speed v1. Sure, no problem. Okay, fine. Mass of a sphere is m, radius of a sphere is r. Okay, fine. And length of inclined plane is L. Okay, now in the next statement, it is saying that the speed of particle at the bottom of plane is v1. Okay, in the first case, speed becomes v1 if the angle of inclination is 45 degree. Now we are changing the angle of inclination from 30 degree to 45 degree and keeping the L same. L is being same. The new speed of sphere at bottom becomes v2. So if you talk about a second case, let's say this is the incline. We have changed nothing. We have just changed the angle of inclination and we have made it 45 degree. The sphere is same. Radius r, mass m, length of incline is also same. That is L. Okay. A sphere when comes here, it has some linear speed v2. Now the question is being asked that what is the ratio of square of their velocities? V1 square by v2 square. This is the question. Okay, I have told one thing that the v is equal to root under, if you consider the formula, root under 2 gl sin theta by root under 1 plus I by mr square, where I is moment of inertia. We understand. For both the conditions, everything is same. Length of inclined plane is same. Moment of body, in fact, body is same. है ना? Both the spheres are same mass, same radius. Both are solid spheres. So we can say that v is proportional to root under sin theta. When a rolling body reaches the bottom point, its linear speed v is proportional to root under sine theta, where theta is angle of inclination. So we can say that v square is proportional to sine theta. V square is proportional to sine theta. So we can simply from this relation write it as v1 square for the first case divided by v2 square for the second case is equal to sine 30 by sine 45 degree. So this comes as sine 30 is equal to 1 by 2, sine 45 is 1 by root 2. So this becomes as root 2 by 2, and this solves as 1 by root 2, 1 by root 2. So v1 square by v2 square basically comes as 1 by root 2. So option A will be our correct answer. I hope this theoretical point of view of rolling motion and this problem solving was easy for you to understand. And from here let's quit this session, and thank you for giving the time. Thank you.